Hello, calculus. Welcome. Today's lesson is on the second fundamental theorem of calculus. It sounds so impressive and so important when we say it's the fundamental theorem of calculus. Good news is this is actually really easy stuff today. I think you will appreciate that. Okay, it's not totally all really easy, but compared to what we've done a lot of times this year, this is going to be pretty easy stuff. We're going to start off with this thing called a function that's going to be defined by an integral. What I mean by that is we're going to have an integral, but instead of having a number in the lower and upper bound, one of them, either the lower bound or the upper bound, is going to have a variable in it. So what we say is that this capital F of x, I could really say anything, g of x, or I could say h of x, whatever we want there. But this function is going to be defined as having the x is either the lower or upper bound of some other function, where this f is the graph here. So we have this graph. In fact, let's just jump into this example. We have a function f in the figure and the function capital F, which really is like the antiderivative of f, defined by blah, 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 blah. All right, so we're going to go from 0 to x. In fact, really up here, this number, since it doesn't really matter, let's just change it to a 0 just to say that this and this are going together. That way you're not confused. I just try to give you an example here of any number. So we're going to go from 0 to x of the function f, little f. So here's my little f. Here's the function little f of t. And we're going to go on the interval from 0 to 4. All the x values from 0 to 4. So what happens if I plug a 0 into x? It's going to go from 0 to 0. Well, if the lower bound and the upper bound are the same, then this is going to be also 0. So the capital F of x. In other words, if I say what's f of 0, that means I'm going to go from 0 to 0 of f of t. That's all I'm doing. And that equals 0. Now let's do it from 0 to 1. What if this was a 1 right here? We plug in a 1, you get 0 to 1. Okay, so here's how we do this. You're probably real familiar with this because we've done it so many times by now with Mr. Brust in units 7 and 8. We're just doing the area under the curve from 0 to 1, and therefore the answer to that is just a 1. So this value right there, that yellow square, is a 1. What about 0 to 2? Well, in order to do this, we need to kind of have an idea of what is this yellow area here, and then also this yellow area. The way I approach these things is I always take the diagonal and I figure out, well, if I just made a rectangle right here, I draw myself a quick little rectangle or think about it in my head, what's the size of that rectangle? Because the triangle is half of it. So the size of this rectangle is 1/2. The base here is a 1/2 and the height of it is a 1. So it's 1/2 times 1 is 1/2. The entire rectangle is a 1/2. Well, and then a diagonal here, these diagonals split it. So in other words, you might need to listen to that again because I was probably really confusing on what I just said. The rectangle's a 1/2. The triangle is half of that, so it's 1/4. And then that means this one is a negative 1/4. Why is it negative? Because it's underneath the x-axis. We're shaded below, so that part of it's a negative 1/4. And while we're doing this, let's just keep going. I'm going to make a rectangle of this part right here. And then we're taking, what's the entire rectangle? Well, the entire rectangle would be 2 squares, so 2 square units. And so the diagonal is half of that, which is going to be a 1. And so I'm going to specifically say that that area is a 1, but I'll make it negative. Now that'll help us figure out this rest of this function. So if I'm going up to the number 2, so if I go up here to 2, I'm going 1 here. I'm going a positive 4th, but then I'm also doing another negative 1/4. So these two cancel each other out, and I'm still at a value of 1. If you plug in a 3 for the upper bound, you're going from here to here, 3. Oh, that's hard. So I know that these canceled out, so I'm at 1 here. I'm at 1 plus 0 because these cancel out. So what do I have just here? Oh, that's really challenging. So I've got, maybe I split it up into these quadrants, I've got half a box there, half a square, and then here it looks like I have another 1/4 of a square, so then plus another 1/4. Oh, let's do my mental math here. This is 2/4 plus a 1/4, that's 3/4, so it's 1 3/4. 1 3/4, or 1.75. Boy, my geometry practice is coming in handy. And then I go all the way to 4. That one's a little easier because this whole yellow thing was a -1. So I'm at 1 plus a 0 and then minus 1. That puts me all the way back to 0. So these were a little tricky, these geometric shapes. I'm not going to give you ones that are quite that difficult, although I will sometimes give you some semicircles where you have to know that the area of a semicircle is pi r squared, and then if it's a semicircle, of course, you have to divide it by 2. So pi r squared over 2. So maybe write that down just to remind yourself the area of a circle, and then divide it by 2 to get the semicircle. Okay, what are we going to do with these values here, these coordinate points? Well, let's answer this question. Where does capital F of x have a minimum? So this represents capital F of x, and you can see here the smallest numbers are 0 and 0. Now, granted, these are only very specific points. Are those really the absolute minimums? Well, if you think about this, if we're starting here, this area is only going up from here. So it's going up, 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 up. So this is the smallest it's going to be. Now the area is going down, 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 down. So that's the smallest that the area is going to be as well. So the starting point there and the end point here, these are both for this particular problem. Those are the minimum values. So when does it have, in other words, at what x values? It's going to have a minimum at an x value of 0 and an x value of 4. So it's 0 and at x equals 4. When does f of x have a maximum? So the maximum point is going to be right here. That's where the area, it's growing, 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 and now it's getting smaller, smaller, smaller. All this area is a negative area. So this is the largest that this integral is going to be, is right at that exact point. So that's halfway between 1 and 2. So at x equals 1.5. All right, integrate this thing. Well, what do I mean by that? We're going to integrate from 0 to x, little f of t, dt. All right, so how do I get the integral of that thing? It is capital F. It's the antiderivative of little f, and we're going to evaluate it from 0 to x. So how does this work? You plug in the upper boundary first. I'm going to have f of x minus, and now I'm going to plug in the lower boundary, which is just a 0. And there we go. So whatever this value is, we're not going to worry about this for now. So this is integrating little f of t. Now what if I take the derivative? So what I'm saying is, let's take the derivative with respect to x of the integral that I just got, f of x minus capital F of 0. Okay, so the derivative of capital F of x is little f of x minus, now what is f of 0? It's a number. We don't even have to know what the value of capital F of 0 is. All we have to know is it's a number and it's a constant. And when we take the derivative of a constant, you get 0. So this number does not matter. It did not matter if this was a 0, if this was a 1. The lower boundary could have been 1,031. It did not matter because once you plug it in and take its derivative, it goes back to 0. So the final answer of that is f of x. Now, why in the world are we doing all this? Some of you are like, Mr. Bean, this is so easy. Yeah, okay, so you take the integral, and then if you take the integral and then take the derivative, you go right back to this. This is the second fundamental theorem of calculus. If you have a lower boundary, some constant, a is a constant, and again, it does not matter what number it is, and you're going to an x, then what happens is if you take the derivative, get rid of this, if you take the derivative of the antiderivative, you get f of x. What? See here how it used to be f of t? All you're doing is you take this x and you plug it in and it becomes f of x. So if you want to know what f prime, this capital F prime is, you just take this x and plug it in. So here, let me show you if you have chain rule. If you have chain rule, in other words, instead of it's just being x, it's g of x. That's highlighted weird there, sorry. Then you have capital F prime of x. You plug in your upper bound, g of x. So this upper bound is your unknown variable. Your lower boundary does not matter. It can be any number you want it to be. And then you have to times it by the chain rule, the derivative of g of x. Okay, important stuff here. Second fundamental theorem of calculus. Get that written down. Let's do some practice problems with this. So here we go. If we want to find the derivative, Then we take the upper bound. I'm going to switch colors. I'm going to take this upper bound variable and you plug it in. So we're going to have 3x squared. Oh, I should write this. I should write technically that we're finding f prime of x, so that we know that's we just are taking the derivative. So instead of going through and plugging in the upper, taking the antiderivative, plugging in the x, plugging in the 2, this is like a quick shortcut that we did right here. See, instead of taking the antiderivative and then taking the derivative, we're just going to go straight to plugging in the number. It is so easy. This just becomes 3x squared plus 4x. You plug in the upper boundary. You don't have to worry about the lower boundary because it's going to be a constant. And once you take the derivative, it becomes 0. And that's it. That's the answer. Oh my goodness, it's the easiest thing we've done all year. Even easier than l'hôpitals. This one, let's plug in x cubed. So now this one's a little different because it's not just an x. When it's just an x, it's the easiest thing we're going to do all year, I think. Now we'll plug in x cubed. Again, this thing does not matter. It's a constant. So you can just like ignore it. Like, who cares? So f prime of x is going to equal, we'll take sine of, now wherever we see a t, we're plugging in an x cubed. So this becomes x cubed. But now we have to times it by the derivative of that upper bound, which is 3x squared. And then typically we could clean this up, and we usually bring those variables in front. So we'd say 3x squared and then sine of x cubed. And that's it. There's our answer. Last one here. 1 to 4x. We're going to take the antiderivative. So we go f prime of x is going to equal, so plug in the 4x into wherever you see a t. So it's h of 4x, and then we're going to have to times it by the chain rule derivative of that upper bound, which is 4. So then this, again, it cleans up to be f prime of x is going to equal 4h of 4x. There's our answer for that one. Boy, this is going nice and quick. Okay. Now we've got two examples that are a little bit trickier, and that's when we have variables in the lower boundary and the upper boundary. So how are we going to do with this? So what we're going to say is split this apart, and we'll say that f of x is going to equal, let's say that this is going to go from negative x to some number that I don't know. Let's just say 0. It doesn't matter what number we use. And then that's going to be of 5t dt plus, now if I start again at 0 and then go to x, I'm using the properties of integrals, where if you just take a number that's in between the lower boundary and the upper boundary, you can split it apart and just say you're adding those two. So what is the number that you choose here? Why did I choose 0? Could I have chosen 1? Could I have chosen 37? Could I choose 50 or 50,126? Yes, the number does not matter, because any number you want is going to be in between these. These are variables. So you just choose any random number, because remember, eventually we're taking capital F prime, we're going to take the derivative, and the derivative of a number is 0. So regardless of which one of these numbers I use, it's the same exact answer. So I don't have to worry about which one it is. So I typically just go with the number 0. That's what most people do, in between the two variables. All right, now how do I do this? We're going to flip it around. So this means we're not taking, oh, let me erase that. We're not taking the derivative yet. We're going to go capital F of x is equal to, let's change these boundaries. I'm going to go from 0 to negative x, and then 5t dt plus 0 to x, 5t dt. But if I switch the boundaries, what has to happen here? If you switch the boundaries, you've got to plug a negative in, because now we're going the opposite direction. So instead of going from negative x to 0, you're going the other direction, from negative x, from 0 to negative x. So that means you make the integral negative. Okay, now let's take the derivative and plug stuff in. So this first bit here, we're going to have f prime of x equals, so I've got the negative in front. I'm going to do an open parentheses just to keep track of what I'm doing here. Oops. And then I'll plug in 5 times, what is it, times by this upper bound, which is negative x. Close the parentheses. And then I have to times that by the derivative of this upper bound, which is -1. Okay, plus. So I just did this first integral. Now let's do the second integral. This one's a lot easier. Just plug in the x. So we get 5x. And then that's it. There's no chain rule on this one that we have to worry about. And then let's clean this up a bit, and we're going to get, let's see here, negative, and a negative is positive, and another negative is a negative. So I've got -5x. And I'm going to say plus 5x. So this combines to be 0. So f prime of x equals 0. There we go. There's the answer to that one. All right, number 5. You're going to pause this one, do what I did for number 4, try and see what you can come up with, and then I will show you the result here in just a second. And voila, there's your answer. Hopefully you can follow my steps there. I try to show every little thing, switch in the upper bound, lower bound, you get in the negative. So you can pause there to try and follow my work if you're not sure how I came up with that. And this is the end of the lesson. Now, most of the practice problems will be like this, and then I've thrown in some extra stuff for you that you're going to see more like what would be on an AP type exam. But that is the end. Hopefully that was easy enough for you. Rock that master check, and I'll see you back in the next lesson.